Ja? Nou goed, welkom allemaal bij de eerste Tatiana Afanassjewa-lezing die we live doen met aanwezig publiek, niet online. Ja, we zijn hier vorig jaar mee begonnen met een lezing van Margriet van der Heijden over Paul Ehrenfest en Tatiana Afanassjewa. En daar kwamen best veel online bezoekers op af. En eigenlijk steeds meer. En toen dachten we gaan het ook live doen. Nou, we hebben Alessandra Silvestri bereid gevonden om dit te doen. Na de lezing, maar we willen ook graag de mensen die het online volgden, die zijn er nu nog steeds. Echt ongeveer evenveel denk ik als hier zitten, of misschien wel meer. 47, ja. En jullie zijn met z'n 51. Die willen we ook de gelegenheid geven om in ieder geval te volgen alsof je erbij bent. Dus we hebben een goede camera geregeld en naderhand zijn er vragen. En mensen die thuis kijken, die kunnen in de chat vragen stellen en dan leg ik die voor aan Alessandra. Nou, Alessandra is wereldberoemd in heel Leiden. Ze is namelijk bekend van Typisch Leiden. Dat is een programma van BNN en VARA over verschillende Leidenaren. En daar zien we Alessandra en haar man Luca Jomi, die hier ook werkt. En hun gezin houden en keren met het academische leven en kinderen en corona. En hebben we ook nog wil ze ook nog hier van ons praatje geven, dankjewel. Alessandra is cosmologe, dus het gaat bij haar over alles, over de hele kosmos. Haar vakgroep is The Late Universe. En dat is niet omdat het nou zo aan de late kant is, maar omdat je richt niet op de oerknal in die ene seconde, maar op de evolutie van het heelal. Hoe zwaartekracht en materie en licht en atoomdeeltjes, of elementaire deeltjes wisselwerken. En dat is jouw onderzoek. Ik denk dat je het zelf eigenlijk beter kan uitleggen. Dus the floor is yours. Dankjewel.
Dankjewel, Bruno. Okay, so goedenavond. And I'm going to switch to English. Apologies for that. But it's too challenging for me to do this in Dutch. Thank you for having me, and thank you for joining also from home. So I'll take this opportunity to tell you a little bit about cosmology, and which is my field of research, as Bruno said. So what is cosmology? It's the study of the cosmos, the study of all those phenomena in the sky that have fascinated civilizations for a very long time. We've been using stars to navigate in the right direction, and we've been amazed by all that we see in the night sky. But it's only when Albert Einstein introduced his theory of general relativity that the study of the universe could be performed with mathematical rigor. So it's only then that a scientific discipline such as physical cosmology was formed. Albert Einstein provided us with this theory known as the theory of general relativity, which is a theory of gravity, and gravity is the main player in the universe. It's the main force that has basically a very important role in the whole description of the universe. So what is general relativity? And you might have heard many times things such as, oh, general relativity, Einstein told us that space and time come together into a four-dimensional entity which is dynamical, and gravity becomes geometry. So matter, the presence of matter, massive objects, deforms space-time and creates curvature, and the curvature of space-time tells smaller objects. Let me try what happens if I do this. Tells smaller objects for instance here, how to move around, and vice versa. So it's all intertwined. Space and space-time become altogether one entity. We have to abandon our point of view of an absolute time and our three-dimensional space. And it's dynamical. So that's how gravity goes on, through these dynamics and the curvature of space-time. It all sounds very fabulous and fascinating, but why would something like this help you study the universe? And in order to explain and show you why general relativity was the key to successful application of physics to the universe, I want to show you a video. So I want to take you on a tour towards the outer universe, because the most important starting point is to change your point of view. Your parents told you perhaps that you are the center of the universe, but you are not the center of, we are not the center of the universe. There's any point in the universe is the same. Every direction, in every direction, the universe looks the same, more or less. And so we have to get out of our very special position. So I want to take you on a short trip out from Earth, getting further, starting to move away. And eventually moving through the solar system, which is really tiny compared to the dimension of the whole universe. So we pass by the sun, and we start leaving also our solar system. So we get to further and further distances. And here there's many more stars, billions of stars, but we are still in a special point. We are inside our galaxy. We have to abandon that as well, get further, assume a sort of distant view. And now you see that our galaxy is just one in trillions of galaxies that are distributed out there quite evenly. So even if things might not look like the same in every direction and the same everywhere, if you're able to take kind of a distant point of view on your universe, it is pretty much the same everywhere in every direction. It is homogeneous, we say, homogeneous and isotropic. There's no special point. And one important consequence, and the first empirical, if you want, confirmation, experimental confirmation that general relativity was really making a lot of sense as applied to the universe, was the discovery by Edwin Hubble in 1929 that distant galaxies were receding away from us with a velocity proportional, with a speed proportional to their distance. So he was able to measure these for a set of nearby galaxies, and plotting here, you see, was plotting as a function of the distance on the horizontal axis, the velocity of several galaxies, or each galaxy is a point in there. And more or less, you can fit a straight line to these points. So that straight line is telling you that the velocity on the vertical axis is proportional to the distance. Now, this was a very important discovery. It came also quite as a surprise, because not only, as I explained in a few minutes, it told us that really going ahead with general relativity as a theory to describe the universe was the right thing to do, but it also gave undeniable evidence that the universe was dynamical. It wasn't just a static entity there. The universe was dynamical, was expanding, and these galaxies, as I show you in the next slide, were moving away from us. So actually, each galaxy is receding from any other galaxy because of the expansion of space, because of the expansion of the universe, with a velocity which is proportional to their distance. And this is really an obvious consequence of general relativity applied to the universe in the following sense. So let us take this universe and let us take this space-time, so this set of 3 spatial dimensions plus our time, and try to place it in our universe. So here it's a cartoonish way of thinking of the universe and the system of coordinates. So you try to label the positions of galaxies, for instance, there in the universe. You construct your old-fashioned X, Y, and Z coordinates. So everything will have a position in there. But what you do, you let the system of coordinates to be dynamical, to change in time. So it's not a fixed grid, but it's a grid that can contract or expand. And in particular, what we see is that it expands. We like to call this system of coordinates that evolves together with the universe. It's like if you, in a very cartoonish and simplistic way, it's like if you draw a grid on a balloon and then you inflate the balloon. The grid will expand, right? But the point where the different lines intersect will be the same. So if you do that, then we like to call this system a system of co-moving coordinates, coordinates that move together with the universe, expands with the universe. So then what happens is that if you have a galaxy sitting at a given point x1 in your system of coordinates, and it's also x1 here, and it's also x1 here, that's the one point. I'm not changing the system of coordinates. I'm letting it expand. And there is another galaxy. I don't have it here, but sitting at some distance at another point x2. Because of the expansion of the system of coordinates itself, the distance between x1 and x2 will change with time. And we call this quantity, this distance, this factor in between x1 and x2 that changes with time, the scaling factor, the scale factor. And it contains all the information about the expansion of the universe. So for 2 galaxies that are in a point x1 and x2 on this grid of coordinates, what we call the co-moving distance, so if I ask you how much is x1 minus x2, that will be a given number. It doesn't matter if your system of coordinates expands, those 2 will be still x1 and x2. But the actual distance will be something proportional at any given time, proportional to the value of this scale factor. So if you do some math, I went too fast here. Now, if you ask, okay, so if I have a given galaxy, I'm sitting in x1, there is another galaxy in x2, and if I want to look at how the distance of this galaxy, how fast the galaxy moves away from me, how does the distance change with time? And so you divide the distance by time, and then if the only thing that can change is this scale factor in here, x is fixed, this distance here is fixed. So you get that the distance is, the velocity with which the galaxy is receding from you is proportional to the distance. Because it's something like the proportional to the expansion rate, so to the rapidity with which this scale factor evolves in time, times you do a little math, you plug in here and there a factor of a, but basically what you get is that the velocity is proportional to the distance, and there is an important factor in front there that we call it the expansion rate. It tells you tells you a lot about how the universe evolves and how the system of coordinates is evolving in time. But so what Hubble observed is really consistent with having a dynamical system of coordinates, something that can evolve in time. Now, of course, I'm making it very simple. There's a lot more that GR tell us, because as I told you, matter and geometry are intertwined. So really, it's not just the galaxies are sitting there like right there and are passively subject to this expansion, but they actually determine the rate with which this expansion happens. And that I will get to that later, but that's also about what general relativity tells us. So this constant, for now, let's assume it's a constant, this quantity in here, which is the expansion rate, the rapidity with which the coordinates expands, has a name, and it's basically the holy grail of cosmology. We call it Hubble parameter, and it contains a lot of information. about our universe, about its history, and about the content of the universe. So I will mention the Hubble parameter several times today. Now, in reality, what Hubble observed wasn't really the velocity of galaxies. We don't observe velocity, we observe what is called redshift. So all we know, basically, at least all we knew so far about the universe, we infer it from observing light. Observing light coming from distant sources, observing this light reaching us from galaxies, from stars, looking at the spectrum of this light, looking at the composition, at the different wavelengths of the light that reach us from distant galaxies. And you know, perhaps you're familiar with the Doppler effect, so with the stretching of a wavelength, of the wavelength of a wave that is emitted by a source that is moving away from you or coming closer to you. We usually give the example of the sound of an ambulance, whether it's approaching or leaving from you, and that's you do notice such a shift, a change in the wavelength, characterizing the wave. And this happens also for galaxies that sit out there in the universe. So a galaxy that is receding from you will emit light, and just because this galaxy has a velocity relative to you, this light will be stretched, will undergo the Doppler effect. But life is not as simple as the Doppler effect on Earth, because it's not just that the galaxy is moving from you, so it emits this light when it was moving from you at a given velocity. It's also that by the time that the light that was emitted reaches you, the time it takes for this light to reach you, the universe kept expanding. So this light is kind of trying to travel through a space that is expanding under it. And so that basically adds an additional stretching. So we always talk about redshift in cosmology. Redshift for a cosmologist is everything. It's an indication of distance, because simply the further an object is from you, the more redshifted the light will be. But it's also an indication of time, because basically the farther back, the farther you look into, the farther back you're looking, the farther you're looking into the past. You see, the more redshifted is the light that you're receiving from a farther distant source, that you're looking at how that source was farther back in time. So redshift is basically everything, and that was also what Hubble measured. He didn't really measure the velocity. Now, for objects that are very close to us, such as those that Hubble could reach with his telescope, redshift and velocity are more or less the same quantity. That's because basically by the time the light takes to reach you from a source that is not so distant, the actual expansion of the universe is negligible. The main effect is the fact that the galaxy was getting farther from you. But the fact that the farther you look, instead, the expansion of the universe becomes more and more important. So it's important to distinguish between redshift and velocity. Still, as I said, the farther an object, the higher the redshift of this object. So there is a relationship. And there is always this Hubble parameter coming in there. It's just the value of the Hubble parameter today is this famous constant that Hubble measured, the constant of proportionality between velocity and distance. In reality, the relationship between redshift and distance is way more complicated, but contains a lot of information. So this is just an example of how we measure the redshift. So we look at the spectra of the light that we receive from galaxies or stars. There is emissions and absorption lines. And what happens is that for a given source, for a given type of star, for instance, and you know the composition, so you know what type of spectrum to expect, what type of light will be emitted by a given star, you do see that depending on the distance of the star from you, you notice the same spectrum, the same shape for the different emission and absorption lines and the total light that is emitted, just shifted towards the red. That's why we say redshift. Oh, so it's not that complicated to get redshift of objects out there, but how about the distance? in an entity such as the universe, which is dynamical, in which the main player is general relativity, so your space-time is dynamical, there is a curvature of space-time and so on, it's not so trivial to describe and to measure the distance to objects. So we have several ways of measuring distances in cosmology, and one way is by looking at how luminous the objects are. This is basically by what we call the flux rule. And there are some good candidates that we call supernovae. Supernovae are remnants of a white dwarfs that has basically grown has grown matter from a companion star and goes through an explosion. Now, all these white dwarfs, once they reach the maximum mass and then go through this explosion, they are characterized basically by a common mechanism of explosion, which means a common peak luminosity. It's like you have a bulb of which you know the intrinsic luminosity because you know very well what is the explosion mechanism. And then the dimmer you see the bulb, the farther it is from you. And if you know exactly how luminous it is, because you bought this bulb, it's just that you put it farther and farther from you. If by measuring how much light you receive from it and by knowing how intrinsically luminous it was, you can infer how distant it is from you. That's what we call luminosity distance. So that's one way in cosmology to measure distance of objects. So what we do nowadays is use supernovae, which are objects that are very far, that are farther away than the galaxies that Hubble could reach in 1929, and look at the redshift by looking at the spectra of the galaxies that host these supernovae. These supernovae are very violent explosion, very energetic. So here you see a supernova exploding in a given galaxy, and at the moment, at the peak of the luminosity, when it goes through this explosion mechanism, it's basically as luminous as the whole galaxy. So they're very luminous objects, very luminous events. And so we take these events, we measure the distance, and by looking at the spectrum of the galaxy in which they are, we measure also their redshift. And now, just because we like to swap things around, instead of doing like Hubble did, that we plot redshift versus distance, we like to plot distance versus redshift. But it's basically just, it should be a straight line again, right? If we so Hubble had a straight line in here. So distance was proportional to redshift, or if you want, redshift was proportional to distance. Why is it that we find a different thing? Well, it is because the universe is expanding. So Hubble was looking at things very close to us, and the expansion, so basically the proportionality between the redshift and the distance was set by the expansion rate today. Now, as you look at farther away, more back into the past, the whole history of the universe in between when the light was emitted and when you observe it will have an effect on the redshifts of your source. So the farther you go, the more you learn about how the universe has evolved in time, about this Hubble parameter as a function of time. And now we say Hubble parameter is a function of redshift because, again, redshift and time are more or less the same thing. So Hubble really was doing things doing things correctly. It was just here and here. So if you zoom in there, there is actually a straight line. But there's a lot more that we can learn if we go to higher redshift as we can do today. So very far, much further objects. So something went wrong here, but so as I said, what Hubble measured was the Hubble parameter today. So its value at redshift 0. Today is redshift 0 in cosmology because if something is emitted just today, you don't observe any reshifting of the light that you receive from that event. So that's basically what we measure. And why is this Hubble parameter so important? Well, as I argue, there's all the dynamics of space-time, all these things, all this fact that the coordinate of system is dynamical, the universe is expanding, and the way the universe is expanding is determined by the matter and whatever is inside the universe is all contained in this H of Z. But also H0, the expansion rate today, so the rate at which we are expanding nowadays, is very important because it tells us a lot of things. And one thing that it gives us is also an indication of the age of the universe, and also an indication of the overall size of the visible universe. We don't know if the universe is infinite or what, but we know that we can see a finite, huge, but a finite patch of this universe. And that size is set is proportional to this parameter H0. Now, so this was the beginning. So Hubble measurements have improved a lot. We have these wonderful Hubble diagrams. We have learned a lot about from them, but also many other measurements. So basically, general relativity was introduced a century ago, and since then, in particular in the last decades, we made a lot of progress. So as I said, cosmology is a physical science. So what we do, we have now a mathematical framework, that of general relativity, to apply to the universe. We can make predictions, but we can also make measurements. That's the important thing. And there's many things that we can measure out there. I will show some of them. And by measuring and combining that with our mathematical description of the universe, we've been able to learn a lot. And the one thing, the simplest thing that perhaps you can infer from what I told you so far, is that if you have a universe which is dynamical, and we have convinced ourselves that because the light we observe is redshifted, it is dynamical in a sense that it's expanding, it's not contracting. So if you try now to play that backward, and you cannot, the universe is a wonderful lab, except you cannot stop, rewind, turn and do it and run it again, but you can do it in your mind, right? And you can do it with numerical simulation. So if something is expanding, now it means that back in the past it was much denser and much hotter. So we have a given density of galaxies out there, and just if you think again of that simplistic version of the balloon with the galaxies sitting in there and the space expanding, then it means that back in the past, whatever matter was in there was much denser. Still perhaps homogeneous in first approximation, much denser, and usually denser means also hotter state. And then from this hot and dense state, what you expect to see an afterglow. You expect to see some light that is a sort of thermal emission from this very hot and dense initial state. So that was the conjecture of what is known as the Big Bang universe. The fact that somehow it started, we don't usually, at least I don't usually address what comes before here, but there was this Big Bang, there was this very hot and dense beginning with a very rapid expansion, and then eventually the universe became very diluted and colder, and as expansion goes on, it gets colder and colder and more diluted. Now, there is a time in which, but in particular, there is a special time in which the light is emitted. There is this afterglow emitted by this very hot and dense early universe. And we have picked up that light. So that is when, so the beginning we like to call it, it's a hot soup of all the elementary particles that you know. And you basically go from very high energies down to, as it expands, it starts cooling down, and then nuclei forms, and then atoms forms. So the beginning, before atoms are able to form, you have a lot of elementary particles that are bumping here and there, moving at very high speed. And so basically an atom forms and breaks, atom forms and breaks, atom forms. So it's a crazy world. But then at some point, the universe, while the particles are doing that, the universe under their feet is expanding, and it is making interactions harder and harder to happen because things get farther away. And also the temperature, the overall temperature of this soup of particles gets colder. So as the temperature gets lower and things get more diluted, atoms eventually form. So it means protons and electrons get together, and photons are free to travel away. Before they were entangled in this crazy soup. And photons are released. That's when we think photons are released. So that's basically the first picture, snapshot that we get of the universe. Before that, we cannot really see that much. And if this whole story of the universe that is nice, homogeneous, and expanding with a given expansion rate, etc., makes sense, we should be seeing this remnant. We should be seeing this afterglow, this light reaching us from when photons decoupled, we say, from the rest. And we do see it was picked up by chance, sort of, in 1964 by some radio astronomer, Penzias and Wilson, in the US, that were trying to do something else, but they had a really annoying noise in their antenna, and they couldn't get rid of it. They tried everything. Then they found even a nest of some birds on the antenna, so they were really happy. They thought that was the source of this noise. And they described it as an odd buzzing sound that came from all parts of the sky at all times. So eventually they realized, by basically word of mouth, talking with other colleagues, that that was exactly the Big Bang afterglow. This was exactly the photons from the early universe reaching us from any direction in the sky with the same temperature from in any direction. So this is the first basically shot of the first image of that, and you see just if you remove our galaxy, which kind of creates a barrier, and if you pick up these photons reaching us from in any direction, this is what you see, a very uniform temperature, photons that reach you with the same energy in any direction from the sky. So that further convinced cosmologists that they were on the right path. Now, again, back to another image of the expansion of the universe. So we start from the Big Bang, and as I said, photons was free. We receive this light, but then expansion keeps going. And eventually we get to the times when galaxies form. Now I'll tell you a little bit how this galaxy formed, because so far I told you a story of a very boring universe, something that is very uniform, looks the same everywhere. How do you get all these clusters, all this structure that we see around us that is not so uniform after all? But the point I wanted to make here, that I've already sort of made, is that the story of the universe that we have built is that of something that is huge and thus being evolving and expanding for something like 14 billion years. So it's a very old universe, and through this expansion, it spans a very large range of energies, temperatures. So you start from something that is very hot and dense, and you get to something that eventually is colder and of lower temperature, lower energy. So what that means, I get back to the point of having a fabulous lab at our disposition. It's very it's rare that you can, with basically one object, of course the universe is already an object, but that you have one entity where you can probe many different regimes of physics. Because in here you can expect that the quantum aspects of physics, because of the very short distances, the very high densities, high temperature, quantum aspects of physics will be very important. General relativity is crucial, but as you basically cool down, expand, and things get farther away, you go towards a more classical regime of physics, and eventually you can apply even some Newtonian physics to understand something about galaxies today. So it's again, it's something that has the downside that you cannot stop and run it again. You have one universe, you don't have an ensemble of many universes. This is the one we were given, and it keeps evolving. But there's many, many different ways in which we can observe things and kind of get access to energy ranges that are very rare. Also, the density changes by a humongous amount of so this cosmic microwave background is this uniform radiation that has reached us, and we call it cosmic microwave background because these photons were released with a given energy at a given characteristic temperature, but then the universe has kept expanding while these photons were trying to reach us, and they have redshifted away, so they basically now it's light in the microwave band. And now, when it was detected, yeah, it was this background of photons with the same temperature from any direction. But now, with better instruments, we could really measure with better precision the temperature of these photons and start to unveil some small differences here and there. So you see the evolution from when it was first, they look at the temperature of the photons with better precision in the 90s to when we did it just a few years ago in 2013 or so with the Planck experiment, but also WMAP, this other experiment in here was crucial. So it's not exactly the same temperature everywhere. If you look at photons reaching you from different directions, there are fluctuations, there are differences in their temperature, but they are tiny, something like 1 in 10,000, 100,000. So it's really very small difference, but it's crucial. There's a wealth of information, a wealth of physics, a wealth of information about the universe that we have learned from there. And it's also these tiny variations in the temperature are really the seeds of the galaxies that we observe today. Because in this hot soup at the beginning, tiny variations in the temperature of the photons corresponded also to tiny variations in the distribution of massive particles. And then under gravitational instability, because of attraction, gravitational attraction, these initial slightly overdense regions started to grow more matters towards them. And so is displaying or not? Probably no. And if I do this, it goes, okay, there was a very, I don't think we need the, maybe I can try, it's a very short animation. Yeah. So it is quite homogeneous, very small fluctuations at the beginning, very small differences in the distribution of masses here and there. But because of gravitational instability, the attraction of gravity, these small fluctuations grow and eventually form the structure that we see around us today. So we sit in one of these highly dense regions. And we have mapped that. So there are experiments. So besides looking at these photons, we have also been looking at positions of galaxies out there. And you should think we are more or less here at the center, and we are looking at, you see redshift, we always use redshift. So that's a distance, basically, right? So we have been measuring all dots there are galaxies. Now, don't ask me the difference in color. It's different types of galaxies, which is beyond my knowledge. But we have been mapping billions of millions, and we are mapping billions of galaxies out there. So it's like we have a huge census of how many galaxies are there and how they are distributed, and it all makes sense. So I can sort of do a match with the map of the temperature of the photons. And it all makes sense from those tiny fluctuations we get to the galaxies today. So now, this was all the nice part. And basically to tell you that we have understood a lot about the universe, general relativity, and a little bit of other ingredients from physics have allowed us to build a consistent story of how the universe started, evolved into what we observe today, understand more or less the age of the universe, and so on. And we have a model of cosmology, which is this, which means we have a framework, that of general relativity, some fundamental particle physics, and few free parameters, few things, numbers that you can tune here and there. And we describe all observations, all the things that we have observed, positions of galaxies, temperature of photons, and so on. They all make sense, are consistent with theoretical predictions given a model. Though there's some puzzling aspects about this model of cosmology. So now comes the challenges and the unknown. We can make sense of all that we observe around us, and we can explain it using the theory of general relativity, as long as we accept that only 5% of what is out there currently in the universe is ordinary matter. So things we are made of, it's the type of particles and type of matter we are familiar with. The other 95% is unknown to us. Indeed, 1/3 of the universe currently we think is in the form of some perhaps heavy particle, some what we call dark matter, something that we don't see. Dark is there for the fact that we don't see it in the standard way, it doesn't interact with light, but we notice its gravitational effect. We need it in order for galaxies to form, to have enough pull, gravitational pull, for the galaxies to then, for matter to fall in there and then eventually form galaxies. Even more mysterious is the other 2/3 of the universe. And that we call it dark energy. And it's something we don't really have a clue about, but we really need it to permeate the universe and explain the accelerated expansion. So far I've been talking about the fact that the universe is dynamical and is expanding. I haven't really commented about the rate at which it's expanding. So I'll now tell you a little bit about these two unknown ingredients. Now, dark matter, as I mentioned, we know it's some form of matter that is out there. It's very massive, it interacts very little, but it creates a lot of mass to kind of aggregate things together. And it was first kind of postulated in the 80s when people observed rotation curves of galaxies. So they were looking at, for instance, the rotation speed of stars around the center of galaxies, and plotting it as a function of the distance. And here in the center, you see the matter that they thought the galaxy was made of, just by looking at light coming from the galaxy. And the velocity didn't follow the expected behavior. It wasn't falling off. So it means that there is more matter out there in the galaxy that we don't see. It's not luminous, but it's sustaining this velocity of the speed of the galaxy, the stars. There is a more modern way in which we can map, and we are convinced ourselves of the existence of this dark matter, and also we know more or less how it is distributed, which is the gravitational lensing, the bending of light by mass. So that's another thing that general relativity tells you. That's what Eddington measured in 1919. So light is bended, and we have that on a nice formula in Leiden, by an intervening mass. So if you look at the light coming to you from a distant source, but in between you and that source there is something massive, the light will be deflected. And we can measure that. So in here, you can tell, even though you don't see it, we only can see with light all this luminous standard matter, ordinary matter, you can see that there is a sort of alignment of distortion in the shape of the galaxies around some center in here. And we use this to tell that there is something very massive in there that we aren't really seeing in light, but we are seeing the gravitational effects because of this alignment of galaxies around it. But the other more mysterious thing on which I work actually is that of the dark energy. So still Hubble diagram. In 1998, so I mentioned supernovae, and by looking at this Hubble diagram for supernovae, so again here it's redshift on the horizontal axis and basically distance on the vertical axis, two independent teams found that actually the way this relationship between redshift and distance was behaving was characteristic of a universe that was not only expanding, but had some billion years ago, it started to do so even faster and faster. So it had entered a phase of accelerated expansion. And now that is really kind of surprising us, because if we very naively think that, okay, there is this explosive beginning, there is this expansion with this Big Bang and this very fast expansion of the universe, but then there is matter sitting in there. Eventually, because of the gravitational pull of matter, we think that the expansion of the universe will slow down. That's a very cartoonish way of thinking about it, but if you apply the laws of general relativity to a universe filled with massive matter, that's what you will get. It will eventually slow down. Now, we don't see that. We see that it was slowing down, but some billion years ago, it has started to accelerate. It has started to expand faster and faster. This is how they thought Einstein would react to this discovery. So, what is sourcing this acceleration? How am I doing on time? I lost the... Oh, okay. What is sourcing this acceleration? We don't know. But there is a nice analogy with something that we learn in the solar system. So by looking at orbits of planets, at some point, Leverrier was able to postulate the existence of a planet that had not been seen yet, Neptune, but was then eventually detected. Thanks to the calculation of Leverrier, he was looking at these discrepancies in the orbit of Uranus, and then he was able to tell that, well, we can understand why the orbit of Uranus is going like that, because actually there is another planet, we haven't really detected it yet, but it's disturbing this orbit. And because of the calculations that he did, he could tell exactly, go there and you'll see a planet right there. And they found it. There were other discrepancies in the orbit of Mercury. Things that we couldn't really understand well using Newtonian gravity to describe the orbit of Mercury. Leverrier tried again to postulate the presence of an unseen planet. But it wasn't that. We had to change the laws of gravity. We had to upgrade from Newtonian gravity to general relativity. So that's very similar to the situation we have nowadays when we try to address cosmic acceleration. We don't really know if there is something out there which is really dark, evenly distributed, and everlasting, in the sense that the density of this something is constant even as space expands. So it's like it's something that is created continuously, it's some energy of the vacuum, or it's simply that we are sticking to some laws that are not entirely correct. Maybe we need to upgrade a little bit, not so dramatically as from Newtonian to general relativity, but we need to upgrade a little bit our theory. So we are trying all those things, and now I'm not going to show you all the things that we try in terms of theories. There's many, and I like to say that there's virtually no limit to a physicist's imagination and creativity. So in the 20 years since the discovery of cosmic acceleration, we have come up with many models that try to postulate some dark energy, some modifications of general relativity, etc. But an artist that was once a mathematician put it all nicely in a painting. And we have this painting here in the building. So, but this is to be solved. It's an open question for cosmology. And maybe I'll go, I'll skip a little bit of this, but just this slide. So how do we go after understanding what is the right theory and what is the right source of cosmic acceleration? Any model that we make up, and that's the basics of physics, it's that it has to have some predictions that then you can go and test. And we do that also in cosmology. So we make our model of the universe, and then we predict where the galaxies should be. And we make many models, and depending on the model that you use, your simulations will show you slight differences in between the distribution of the galaxies. And in principle, with upcoming missions, we're gonna map so many galaxies with such a precision and looking at the bending effect that they have, that we should be able to discern among all the different models, and ideally, hopefully, understand more about what's going on there with these large scales and this cosmic acceleration. Now, I'm going to skip this because I think I need to Finish, right? Okay. So I said a lot about redshift, and we have learned a lot about our universe from light that we receive from distant sources, and that was all until a few years ago. Now there's a new way in which we can learn something about our universe, which is gravitational waves. It's a new window, if you want. So I'm gonna just play this short video. Yeah.
A new observational window on the universe typically leads to surprises that cannot yet be foreseen. We are still rubbing our eyes, or rather ears, as we have just woken up to the sound of gravitational waves.
So a few years ago, we were able to detect gravitational waves. Now, gravitational waves are the true dynamical aspect of space-time. They are disruption of space created by very violent events that are non-spherical, such as two very massive objects that orbitate around each other and eventually collide and merge. So, for instance, two heavy black holes eventually in spiraling and merging into a final black hole. Such asymmetrical and violent massive events disrupt the system of coordinates that you have out there. So disrupts heavily the geometry of your space-time, and you can see that through waves that propagate and eventually reach you. And if you set up an interferometer like this with two arms, what these waves, if the Earth is hit by such a gravitational waves generated by an event, these two arms will be slightly deformed in length at a different rate. And you can pick that up. It's something crazy to do, very difficult, but they've done it. Now, the only point I want to make before I stop is that we don't see gravitational waves, we hear them. Basically, we basically reconstruct the way these arms oscillate in reaction to the passing of the wave, and you can hear this sound that appears in the detectors. Now, but they're still waves. They still carry away energy. So again, I can repeat the exercise of understanding. If I know how energetic the initial event was, and I measure how much energy I receive, I can infer how distant the event was. And if there is also light emitted by this event, which is not always the case, and I pick up that light, I can also know the redshift. So another indication of distance, but you remember between redshift and actual distance, so there is the whole expansion of the universe, expansion rate. And so now we have these new objects out there. There are not as many as supernovae yet, but there's been many, many of them. And they're helping us understand more about the Hubble parameter. I didn't really spend that much time on that. So, but just to say, we have something like 60 or more gravitational waves that have been detected with the presence of 2 interferometers in the United States and 1 in Italy. Now there's Kagra in Japan that has turned on. There will be eventually 1 in India turning on. And the more you have, the better you localize the source of the gravitational wave. And we will go to space. This is the next exciting frontier, launching imaginary arms, 3 different satellites, moving following the Earth in its revolution around the sun, and picking up these possible, actually not possible, there are many, gravitational waves out there in space. And I think I'll stop here, and thank you for joining.
Wel, heel een enorm overzicht van het Hubble. Eén ding, we hadden wat technische problemen aan het begin. we moeten er wel om 9 uur echt buiten staan van de portier.
Ja.
Oh. Dus komen we niet meer buiten. Nee, dat weet ik niet. Maar toch is wel tijd voor 1 of 2 vragen, denk ik. Uit het publiek. Ja, meneer daarachter.
I have a question about the speed of light. You told that objects, when they are far away, are traveling with a higher speed. Is it possible to reach the speed of light? The distance is far enough.
Yes.
Other question I have is speed of light still absolute in an expanding cosmos?
Those are brilliant questions. Yeah, so speed of light is a fundamental quantity, is at the heart of special relativity in particular. Of course, it plays an important role in general relativity, but it's as you kind of already understood by yourself, the fact that we have a dynamical space-time. So we have this expanding universe, and where curvature also plays an important role. That basically means, in very technical terms, means that we are not able anymore to have an overall inertial reference frame. Okay, so speed of light. So it is possible, if you want, it is possible in principle for things that are sufficiently far away to actually, just because of the expansion of the universe, to have a recession velocity which is higher than the speed of light. But there's no breaking of any of the things that we usually associate to the absoluteness of the speed of light, such as causality, because it's a very different environment. I know me and this object that is receding away at the speed faster than the speed of light, we are not in the same inertial frame. It's very difficult to connect us, and this object is most of the time, while it's speeding away with something that is faster than the speed of light, it's really just sitting there with a very small velocity. And the fact that it's moving with faster than light is just due to the expansion of space where it lives. So yes, it is possible, but it doesn't, and speed of light has still a very important role. But on the global scale of the universe, where curvature is very important, then it's not so easy and straightforward. So there's no breaking of any causality. Ja.
Oké, dank u. Er was ook een vraag van de online kijkers, waarvan er 47 waren, zag ik. Dus best nog druk hier. En dat is de vraag van Maarten. Hoe volgt uit de algemene relativiteit dat A dot over A constant is? So why does this goes back I think to your bit of math in the beginning. So yeah. why is A dot over A constant?
Yeah. It's not. So it's a constant when I look at things that are very close by. So today, so it's the expansion rate at any given time. It was constant for Hubble. So yeah, I was cheating a bit in that math because I was doing it. So that it is not a constant. It is a constant if you're doing it at a given time. So if you're looking at objects that are very close to you. And that was the Hubble constant. Otherwise, it is this h of z, so it's this evolving quantity. Yeah.
Okay. Well, one more.
Well, what's the difference between Leiden and Leiden? I've heard there's also Leiden.
That I don't know, honestly.
European Leiden.
There's a LISA pathfinder.
That happened.
Yeah.
And that was very important in particular. So these satellites have each inside, they have test masses, and you basically want to see how the motion of these test masses inside are affected by the passing of gravitational waves. And I think the Pathfinder explored whether that could work.
Yeah.
ELISA, yeah, I'm not sure. Sorry, I'm not sure if it has to do with some funding or whatever. It is mostly an ESA mission, but there is also participation by NASA. I don't know if there is.
Oké. Alessandra, ontzettend bedankt voor je verhaal. ja, we komen volgende keer weer kijken, anders online. En nou moeten we snel naar buiten. Bedankt.